All right, welcome to The Explainer. Today, we're diving into a really cool breakthrough in AI that tackles a fascinating puzzle. How, exactly, do you teach a computer to spot a flaw that it's never, ever seen before?
Think about it. How can a machine possibly find a defect, a tiny scratch, a little crack, maybe a missing part, if you've never actually shown it what that specific defect looks like? It sounds almost impossible, right?
Well, in the world of high-stakes manufacturing, this is a huge deal. They call it the cold start problem. And it's a problem because, let's be real, collecting examples of every single thing that could possibly go wrong, that's just not going to happen. So the whole game shifts. You have to teach the system what's perfect so it can flag anything, and I mean anything, that isn't.
Okay, so how did people try to tackle this before? Well, the early attempts had some, cracks in them. They ran into this really fundamental bias that really held them back. So, the old way of doing things was to use these really powerful AI models, right? But here's the catch. They were trained on these massive databases of everyday photos, stuff like cats, dogs, cars, you get the picture. And the problem, the really big flaw, is that the visual cues an AI learns to tell a cat from a car are just totally different from what it needs to spot a microscopic scratch on, say, a metal screw. It's like asking a world-class chef to fix a car engine. Wrong skill set. This ImageNet bias meant they were basically looking for all the wrong things. But that limitation, that whole ImageNet bias thing created the perfect opening for a new hero to enter the scene. An algorithm called PatchCore. And it approaches this whole problem from a completely, fundamentally different angle.
Yeah, so instead of using all that irrelevant knowledge about cats and dogs, PatchCore does something brilliant. It builds what you can basically call a visual library of perfection. It only looks at pictures of good, non-defective products, and it learns every single nook and cranny of what that perfect product is supposed to look like. It becomes the ultimate expert on normal.
So what's the secret sauce here? How does it build this library and then use it so darn effectively? Well, it all boils down to a really elegant three-step process. It's simple, but it is incredibly powerful.
The whole logic is actually pretty straightforward. First, instead of trying to look at the whole item at once, the system breaks it down into these little tiny pieces, these visual chunks or patches. Then, for step 2, it analyzes all the patches from all the perfect items and stores their key features in that massive database, our library of perfection. Finally, when a new item comes along for inspection, it does the same thing, breaks it into patches, and then for each patch, it asks a really simple question. Hey, have I seen anything that looks like this in my perfect library? If the answer is a big nope, bam, it's flagged as a defect. Simple as that.
Okay, but wait. There's a catch, right? There's always a catch. This creates a brand new problem. If you store every single patch from thousands of perfect examples, well, that library becomes absolutely gigantic. We're talking enormous. Searching through that on a fast-moving factory floor? No way. It would be way too slow and clunky. So to fix this, PatchCore has another trick up its sleeve. It's a really clever technique called core set subsampling. Now, you could just pick patches at random, but that's kind of like hitting shuffle on a giant music library. You're going to miss a lot of good stuff. Instead, core set sampling acts like it's creating a greatest hits album. It intelligently picks out the most representative patches, the ones that capture the full diversity of what normal looks like, but without all the redundant filler. You get the whole vibe, but in a much, much smaller package that's super fast to search.
Okay, so the theory sounds great, right? A greatest hits of perfection. But does this new approach actually work any better? Well, as they say, the proof is in the pudding. Let's look at the numbers because they are seriously impressive. Check this out, 99.6%. That is the score PatchCore got on a standard benchmark for just identifying if an image has a defect or not. That's practically perfect. It's an absolutely astonishing level of accuracy.
But let's put that number into context because that's where it gets really crazy. Compared to the next best competitor out there, PatchCore literally slashed the error rate by more than half. Think about that, going from a 2.1% error rate down to just 0.9%. On a factory floor producing thousands of items an hour, that isn't just a small improvement, that is a massive leap in reliability.
And here's the kicker. It's not just more accurate, it's also faster. You'd think with this clever, greatest hits method, it might be slower, right? Nope. That smart, core-set-reduced version of PatchCore is actually quicker than its main rivals. So you get better accuracy and higher speed. That's the holy grail for any real-world production line.
And if that wasn't enough, it's also incredibly efficient with data. PatchCore can get these amazing top-tier results with just a handful of good examples. Get this, in one test, it performed just as well as the previous best method, but using only 1/5 of the training data. That is a total game changer, especially when you're setting up a new production line and collecting thousands of perfect samples is expensive or just takes way too long.
So, let's bring this all home. Why does any of this actually matter? Well, this isn't just some fancy paper in an academic journal. This has real, tangible consequences. For us, it means more reliable, safer products. For manufacturers, it means catching errors early, which saves a ton of money and materials. And that means less waste, which is better for everyone. It's a win-win-win.
And that really leaves us with a big final thought. This whole approach, this shift from teaching a machine what's wrong to helping it deeply, truly understand what's right, it's more than just a trick for manufacturing. It's a whole new way of thinking about how AI can solve problems. And it really makes you wonder, doesn't it? If we can teach machines to find these tiny, unseen flaws, what other unseen problems could they help us solve next?